few words about John Cockerill and myself. So I'm head of strategy for John Cockerill Hydrogen North America. I've been working in the hydrogen sector for more than 8 years now. And John Cockerill is one of the leader electrolyzer manufacturer worldwide. We have manufacturing facilities in China and in Europe, and we're currently building other manufacturing facilities in North America, India, Morocco, and Middle East. And we are mainly producing pressurized alkaline electrolyzers. I'm very glad to see that a lot of people are interested to know more about LCOH and how to optimize the calculation of it. So let's begin the topic right now. And feel free to ask questions through the chat. As Susanna mentioned, I'll try to answer as much as possible. I'll try to keep the presentation short so we have time for interaction at the end. So I wanted to start this presentation on, let's say, back to the basics on just a simplified example of why the levelized cost of hydrogen is a useful tool for you, for your company and for your project. So when you look at this table, you might wonder, okay, for my project, which electrolyzer is better? You have two electrolyzers, one with a cheaper capex, or less expensive capex, but higher energy consumption, which means that you're probably going to need to pay more for electricity to run the electrolyzer, and the other one with a higher capex and higher efficiency. And well, to answer this question, basically, as for now, there is no good answer because it depends obviously on your project. Your project is unique in several ways. So the LCOH will be very specific to your project and the way you're going to design your project. And therefore, the LCOH is going to be a useful tool for you to make decisions on the design, on the type of electrolyzer you need for your specific project in your specific location. So that's just as an introduction. Also, every supplier provides, so not just for electrolyzers, but also suppliers on EPC and other type of equipment like compressors, storage, and so on, provides a different scope with different data and calculations. So you will have to make sure that you're comparing apples to apples when you input this data into your LCOH calculation. So this introduction just to state that there is no electrolyzer supplier or no OEM that can claim to have the lowest levelized cost of hydrogen across all projects, all geographies, all project design, because each LCOH is very unique to your project. So now let's dig in a bit more on how we define the levelized cost of hydrogen. So basically, the levelized cost of hydrogen is a tool that helps you answer that question: how much does it cost me to produce 1 kilo of hydrogen? This answer is not, well, this question is not really easy to answer because there are a lot of different parameters that are linked all together. So as I've shown in my first example, you can have a very high capex for a system, but then the efficiency is very good. So over the lifetime of your project, and depending on your price of electricity, investing more initially could be more interesting for you on the long run and could lead to a lower levelized cost of hydrogen in the end over the lifetime of your project. So the levelized cost of hydrogen calculation is, if we simplify it to its maximum, is dividing all the costs you have over the lifetime project, divided by the amount of hydrogen you are going to produce with your project over its lifetime. We'll dig more into all the details of what's in each bucket, but overall, it's answering and trying to fill as much details as possible in those two buckets. So for the lifetime project cost, obviously you think about the capex, but you also have to account for maintenance and operation. You have to account for energy costs, financing costs, depreciation, equipment replacements, and so on. And in terms of the amount of hydrogen that's produced over the lifetime, it's going to depend on the way you're going to operate your plant. If you want to run it 100% of the time, or if you want to do cycling on and off cycles, It's going to depend on the technology efficiency, the size of your plant, obviously. So we'll dig in more into these details in a few minutes. But before you do and you start your calculation, I think what's really important is for you to well define your scope and the level of detail you want to put in this calculation. So as I presented, you can do a very simple simplified calculation, which is what's at the bottom of the graph. For example, if you want to very quickly compare one technology over another, two products very quickly, you can use a simplified calculation for LCOH, and you don't need to add much more details to it to find the breaking point at which one technology is going to be better for your specific project. But then so that's if you want basic calculation. But then if you want, for example, to use this value of the cost of hydrogen for your project to input that in your financial plan, for example, for investors, or if you want to know how much it will cost you to produce hydrogen, so then you can sell it to a customer, and you need to establish a contract with this off-taker, you will need to have a very precise and detailed LCOH calculation that encompasses all costs and all details to be as close as possible to the real cost of how much it's going to cost you to produce this hydrogen in reality when your project will be up and running. So the way I see it is that you can start with a very simplified calculation and then add on details and more complexity to your calculation to tend towards the most precise real cost of hydrogen. But obviously, as you increase and you add more and more layers and more details, then the calculation of your model is going to be more and more complex, but you will also get more accuracy on the calculation. So as I said, you need to start answering that question: what's my objective when calculating my LCOH? Do I want to have the most precise number for my investors so I can mitigate financial risk, maximize returns when I'm going to sell that hydrogen? Do I want to identify the best technology for my project? Do I want to design my project in a way that's optimizing the LCOH? Or finally, you can also use it once you're in operation to optimize the production over time. For example, if you want to get into a lot of complexity, you can predict the levelized cost of hydrogen and have it as a function of your cost of electricity if you know how much you're going to pay for your electricity in the coming year, for example. And then you can adjust and optimize your operation to meet at all times the lowest levelized cost of hydrogen during your operation. And so I presented, three possibilities or reason for you to want to calculate the LCOH. And I'll just give you an example of how an electrolyzer OEM like John Cockerill is using the LCOH calculation for designing its product. And so it's a very different way than you can use the LCOH calculation for your projects for investors, for example. So for making that calculation, we don't need to input a lot of details about projects, about, financial costs that are very project specific. The idea here is to define the product, select which configuration will be giving the lowest LCOH for our customers under certain conditions. So the graph, for example, is presenting different LCOH costs for different level of energy input. And so the stack, so the electrolyzer system we're producing is composed of a number of layers of different cells. And the more you add cells, the higher the efficiency is. But also the more you add cells, the more expensive your electrolyzer is going to be. So you can see here LCOH as a function of the number of cells and a function of the cost of electricity. And we've run those calculations in several configurations. And here in green, you can see the optimum for the lowest LCOH for each level of electricity. So for example, if my electricity is going to be $80 per megawatt hour, my optimum LCOH is going to be here, and maybe and so this range of number of cells for projects having a $80 per megawatt hour electricity cost is going to be the best design for them. And so this, for example, this tool of LCOH is helping us to select what would be the best number of cells, depending on what we see on the market in terms of energy pricing in different regions, and enable us to maybe develop different products for different geographies where you have different electricity cost. And obviously for that, we don't need to add all the financial details and so on, because what we want to focus on is depending on the price of electricity, what will be the best configuration, what will be the best CapEx and LCOH for my electrolyzer. So now that I've done this example, let's dig more in depth into the different cost factors and all the buckets I've presented in the first slide. So here we are considering all the costs. So that's the top of your levelized cost of hydrogen calculation. So the CapEx cost, obviously you think about electrolyzer, which is probably going to be a big item in your CapEx calculation, but you also have to not forget, if you want to get into a detailed calculation, to add the cost of delivery, the cost of installation, all the EPC costs, so site preparation, civil engineering, construction, labor cost, the cost of power connection, cost of obviously the balance of plants. So maybe you will need to have storage tanks, maybe you need to have additional compressors, instrumentation, and so on. And that will add up to your CapEx. And just before I go further, I just want to add a comment on that. So these costs are going to be very much linked to the design of your project. So for example, if your project is close to an electric substation, your power connection, and in a region where power connection costs are low, you don't need to add another line to connect the substation to your project, then your power connection costs are going to be lower than if you're in a remote place where you need to add substation, you need to add a line dedicated to your project to connect your project to power. And that's going to be the same for everything else, like water supply for producing hydrogen, but also what you're going to do with your hydrogen after production. So if you need to set up a pipeline, if you need to store it, it's going to add up on cost. And this is really linked to your project and not about the type of electrolyzer you're going to select. So that's on the CapEx cost, and then on the operational and maintenance cost. Obviously, you need to think about what's going to happen during the whole lifetime of your project. So you need to plan for inspections, repairs, replacing components, refurbishing the stack, for example, integration of renewable energy sources if you want to add additional connection, energy storage, grid integration, utilities. So I talked about water, so you need to account for the water cost, the energy cost, and so on. In that bucket, as same as in the capex cost, as when you're doing the first assessments of that, sometimes it's better if you can have, like, for example, an EPC who is working with you on the project and can provide you with an overall estimate of, for all the EPC work, construction, installation, and so on, how much it will cost for your project. And same for the operational and maintenance cost. You can have long-term service agreements in place that will take care of most of the parts for, like, operational and maintenance, inspection, repairs, and so on throughout the lifetime of your project, and also guaranteeing that you will get the expected availability, performance of your system throughout the whole lifetime of your project. So that was for the cost. Now let's get into the production factor. So that's the denominator of your LCOH calculation. And basically you want to ask yourself how much my project is going to produce hydrogen every year or over its lifetime. And this is going to be dependent on obviously the size of your plant. That's kind of basic, but also the way you're going to design and configure the whole setup of your plant. And it's going to be also dependent on the way you want to operate your plant. So for example, if you plan on operating your plant most of the time, let's say 96% of the time, and you will need to have a stable power input to your plant, then you will have, the amount of hydrogen that's going to be produced is fairly easy. But you still need to account for scheduled downtime, unplanned downtime, throughout the lifetime of your project. For example, how long is it going to take to replace an electrolyzer for refurbishment? How many hours of maintenance are required every year for which the whole plant needs to be shut down? And you need to ask yourself those questions. Otherwise, the production amount you're going to have is going to be overestimated compared to what's going to happen in reality. So you want to account for as many factors like that, reducing the potential production of your projects as possible. And the other last point, is the efficiency and degradation of the electrolyzer. So obviously you have a certain amount of energy as an input for your project. You have the size of your plant, but then with this specific amount of electricity, if your electrolyzer is more efficient, you will be producing more hydrogen virtually out of your system. So you have to account for this point, and for the degradation of the electrolyzer. So all the performance of your system is going to degrade throughout time, and you need to account for that. You also need, and that's really important, if you are operating in a start and stop mode or with cycling, which means that you probably have an input that's from renewable energy. You will need also to account for, the impact of the start and stop cycles in the degradation of your electrolyzer, but also account for, how long does it take to restart your electrolyzer. Make sure, you can do this ramp up and down and follow the load. And that's some, items and details that needs to be looked after and discuss with your electrolyzer supplier, but also project designer, to see how all this will fit, and then take this data and input it in your levelized cost of hydrogen calculation. These were the basic, I would say the minimum things you need to take into account in your calculation to have the first, I won't say simplified because it's already a bit detailed, but a first good idea of what your levelized cost of hydrogen would be. And then on top of that, if you want to get to the almost as close as how much it's really going to cost you, you need to add additional factors into your LCOH calculation. And so, I mean, these factors, sometimes you will need them. You will need to assess if they are going to impact your project enough to make it worth for you to input that in your model. But for example, financial structure and capital allocation could be a real impact. So if you get your project finance and you have a very high cost of capital, then you might prefer to have lower initial capex in your project, because otherwise it's going to impact much more your levelized cost of hydrogen. And then again, this is something you can change. If you see that your cost of capital is too high, you can think about other options for financing your project if those options are available to you. Environmental regulation and compliance costs. So I won't list them all, but if there are carbon pricing systems in your region, if you have incentives like subsidies related to CO2 emission reduction, all these aspects could be taken into account in your model to account for it in your levelized cost of hydrogen. I've already talked about hydrogen storage and distribution costs. So after the production, purity requirement, which is also a technical basic. And some things that we don't think about much is the construction duration and project timeline. So these can also affect your LCOH in the sense that so LCOH ideally is going to account for the time value for money. So the longest your duration construction is going to take, and depending on the project timeline and when you're going to make investment for your equipment, this can affect your LCOH calculation as well and the true cost of your hydrogen. Market dynamics and demand supply dynamics. So this is also something that's a bit more complex to account for, but I briefly touched the point earlier on your electricity cost. So your electricity cost can be secured over like 20 years on a PPA contract, or with the assumption that the electricity cost will be known over the lifetime of your project. But you can also model some dynamics and input some dynamic in the electricity cost. For example, even like hour by hour accounting for the fluctuation in the electricity market if you are planning on getting your electricity in a free market. And last point is technological innovation and advancements. Your project is going to last 20 years, but it's, and you're going, for example, I'm talking for electrolyzer right now, but you're going to need to replace your electrolyzer every, like, depending on your project, 8-10 years. So you will have at least one replacement to make during the lifetime of your project. And you can also account for, improve efficiency, maybe lower cost of capital for electrolyzers in 10 years than what you can see now. And this will be the same for, all the other technologies, like hydrogen storage probably will be cheaper. So if you need to make some additional investments in that type of equipment, you can account for that in the future investment in your levelized cost of hydrogen model. Now we get to the best part of the webinar. So I just explained basically how to calculate your levelized cost of hydrogen and all the factors that you can take into account in your calculation. But this is very good, but all of this is just pure theory pure theory if you don't have good data. So if you want to have and to show to your investors or project developer partners a cost of hydrogen that's as close as possible as what you're going to get, you need good data, good input data. And for that, you need to know how to compare apples to apples. I know it can be difficult because when you received, quotes from suppliers, they are all different, and the industry is currently very new, so everyone's trying to adapt and to structure in the same way. But you really need to take the time to dig in the data you receive and to input this data in your model in a way that's going to be as close as possible as the reality. So for that, you will need to start standardizing the vendor's data and analysis. And for that, there are also two buckets. One is quantifiable elements, which are like, technical elements like efficiency, and commercial elements like CapEx, OpEx, which are basically numbers, and this is easier to manipulate, I would say. And then the other bucket is non-quantifiable, which is going to help you to assess how much you can trust this data from that supplier. And this comes down to, is the supplier reliable and bankable? Is the supplier reputable? Asking you these kind of questions help you decide by yourself if the efficiency data that was given to you is strong enough, or if it's just overestimated or underestimated by the supplier, compared to what you're going to get in reality on the ground in your project once your project is going to be in operation. Because the least you want is to sign an FID with your investor with very good number on paper. I mean, it's good, but then having your project developed and realizing that the efficiency is not as high as expected, and then your whole LCOH model is, your whole levelized cost of hydrogen and cost of hydrogen for your end customer is not going to be the same as the one you signed initially. So you need to account for these elements. And one of the other reasons why you need to account for that is when you're going to go and check with your investors if they want to sign for your project and fund your project, they're probably going to require a background check on all your suppliers, and they will all need to be strong enough and reliable enough in the view of the investors to grant you the funding of your project. So let's look at some of the main things, and I'll go through. I won't go through all of them because we probably won't have time, and you will be bored by then. But I just want to emphasize and pinpoint some of the big items. So when you want to standardize the scope data point by point, you need to focus on the aspects that are making much impact for your specific project. When you look at the overall levelized cost of hydrogen as it is today, and you put that in a pie chart, you can see that for all the projects, the energy cost is around between 65 and 85% of the levelized cost of hydrogen, which means that the energy consumption aspect, the energy cost, and everything related to energy, like degradation, as I mentioned, energy cost, energy consumption of your electrolyzer, are key items that you will really need to dig in and understand and make sure you're comparing apples to apples and make sure what you put in your model is reflecting the reality. So for example, for energy consumption, you could ask questions to your suppliers, first making sure that the energy consumption is the data of this energy consumption, making sure you understand what scope it comprises. So is it just the stack? Is it also including the auxiliaries? Is it including energy losses due to the different connection between the items? Is it a value that is in AC, in DC? Is the energy consumption data for 100% load of the electrolyzer, or is it for, I don't know, 60% load of the electrolyzer? The energy consumption of the electrolyzer is going to be varying depending on the load of the electrolyzer. So if for your project, for example, you intend to use all the electrolyzers at 60% of their load because for some reason, in terms of like energy supply, it's better for you, you must ask your supplier to provide you with the energy consumption for their system at 60% load. You don't want to use the value at 100% load because it's not going to be, reflecting the true efficiency you're going to have for your project. For the degradation and lifetime, that's another big item. It's same, like degradation is going to be linked as well as on the way you're going to operate your system. So if you're going to operate it with flexible load, with a lot of start and stop, it's very likely that the degradation value is going to be higher. So you need to account for that in your calculation and make sure that the data your supplier is giving you is accounting for it. And then I was talking about the quality of data. So for these two items, energy consumption and degradation, you want to ask, is it something that is guaranteed? Is it just an estimate? Is it something that was calculated, or is it something that was proven on previous projects? You want to ask those questions. You want to make sure that's going to reflect what you want to get in your model and what your investors want to see. For lifetime is the same. So for example, for lifetime, in some cases, you could have higher lifetime for electrolyzers, well, longer lifetime. So you can sometimes even avoid replacing the electrolyzer twice during the lifetime of your project. Depending on the lifetime of your project, you can replace just once. And this is going to save you a lot of costs in terms of CapEx, if it's possible. For flexibility, for example, if you're operating electrolyzer on flexible load, you want to ask a question about, for example, so usually flexibility comes down to the operating range of the electrolyzer, so how much you can reduce the load, and the ramp up rate, so how fast the electrolyzer can adapt to a change in power input. But then, so that's the basic, and that's only for the one stack system. Then you will need to ask yourself, depending on your project, okay, how much flexibility I need? Because if you, for example, need to ramp down a project that's 500 megawatt or 1 gigawatt down to 5%, that's going to be, I don't know, like 50 megawatt, for example, which means that you will need to run at 50 megawatt at the minimum load for your oil plant. And for that, you need to know if you can switch off all of your electrolyzers except 50 megawatt worth of capacity, or if it's better for your operation to just reduce the load of all your electrolyzer down to, I don't know, 5%, 10%, whichever fits to make it up to 50 megawatt. So you need to understand what's possible, what's not possible, and how it's going to impact the rest of the items. So for example, how it's going to impact the efficiency and energy consumption, degradation of your system to find the best way on how to operate your plant given those inputs. We'll just go to the two last items, which are availability and pressure. So same for availability. You want to make sure that when an availability number is presented, to understand what does it mean. Does it include, I don't know, preventive maintenance? Does it include whatever downtime you might have? You want to make sure you're talking about the same thing with your supplier and what's in your model. For pressure, this is the same thing. Some electrolyzers are pressurized, so you can have outputs of 15 megawatt, 30, not 15 megawatt, 15 bars, 30 bars. And depending on your needs for your projects, you will need to kind of standardize these offers to make sure that you add a compressor in your capex when evaluating one option, because this option is atmospheric and won't be providing you with the right pressure you need for your end customer. So all those aspects are very important when you want to make an apples to apples comparison and input good data into your levelized cost of hydrogen calculation. Same for capex, opex, performance guarantees. So I won't dig a lot in those, but capex, capex is fairly easy, but you will need to make sure that what's including, what's not including, is piping included? Are the installation costs included? Is the transport to and delivery included? You want to make, to ask all the right questions about it to make sure you've included everything. And for the OPEX is the same, if you have a contract for operation and maintenance, it makes things easier. Otherwise, you will need to know, how many hours you will need per year in operation, in maintenance for the systems, how many spare parts or components you will need to buy every year or every 5 years or every 10 years for your project, so you can input this data into your calculation. And finally, the other aspects that are less quantifiable, but you still want to make sure you have a good grasp of them. So I've already talked about track record and bankability and how important they are to investors, but also to yourself when putting data in your model. And I'll just go quickly on the norms and standards and the territory coverage. And something I didn't mention that's linked to the data. So we realized that the standards are not well defined today in the hydrogen industry for calculating the hydrogen flow and the hydrogen efficiency. So Western and European, American, Canadian electrolyzer manufacturers are calculating the hydrogen flow by measuring the volume of hydrogen out of the electrolyzers. And that's how mostly, efficiency, capacity of electrolyzer is calculated for those Western vendors. For Chinese vendors, the calculation is done differently because the norm is different in China. So they calculate that using the electricity input instead of the hydrogen output. And by doing that, they are overestimating the efficiency of their systems. And not voluntarily, but that's the way the norm is done compared to Western vendors. So there is an estimation of efficiency by around 10%. and also the way they are calculating the capacity, so the actual volume of hydrogen you will get out of, let's say, a 5 megawatt stack. It's common knowledge that 5 megawatt stacks, it's 1,000 cubic meter per hour. But in China, it's going to be less because of the way they are calculating the flow and the energy inputs. So you also want to make sure when you receive a quote that you account for these different norms and standards between the different regions. Otherwise, you could end up with a totally different conclusion if you don't account for it. And you also need, if you're sourcing your electrolyzer or your system from another country, that you also need to account to make sure that they are providing a system, even like PCU and gas separation unit or whatever, with the norms and standards of your specific country and geography where your project is located. You want to make sure you comply with all of these norms and standards. And if the product is not compliant with norms and standards in your geography, there might be additional costs for them to get compliant with your geography. So this also needs to be considered, and feel free to ask your suppliers about it to make sure everything is aligned with your needs. And finally, you have local incentives. So there are now a lot of countries that have published support for hydrogen production. So you need to account for these local incentives in your model, but also make sure you are going to, in Europe, there are the 3 pillars. In the US, we have the 45V. So you need to make sure that you can get these subsidies from incentives, but also that you are going to comply with all the requirements they're asking you in terms of, CO2 emissions, connection to renewable electricity, and so on. Starting the last part of the presentation, I'll be brief on that. Once you've set up your model and you're ready and all your data is good and well, you can start playing with your LCOH to help to identify the key driver for your specific project. And that's going to be helpful to understand what's driving the cost up in your project and how you can optimize your LCOH, how you can find solution to reduce LCOH to a point that's bankable and that's suitable for your needs. So as you've seen, and that's just talking for electrolyzers, if you change one aspect, if you reduce one aspect, you're likely to increase another aspect, and no solution can be good across all the board, being the most efficient, the cheapest, the most durable, and so on. So obviously you need to balance and to prioritize on which aspects are more important for your project. And that's how you do what you do when you do a sensitivity analysis. So you're going to select a few items that you think are going to be dimensioning or impactful in your project, and then try to analyze how they make your LCOH vary if, for example, you increase them by 5%, 10%, 15%. So, for example, here you have a base case, and the dark blue line is the electricity efficiency. So base case is here 100%. If your electricity is at 100 megawatt hour, if your electricity is 85% of the base case, which means cheaper than initially, how is it going to affect my LCOH compared to the other parameters? And you can see here by moving by 15%, moving down by 15%, the electricity cost is driving down the LCOH much more than, for example, moving down by 15% your CapEx. Just an example on how you can use it as well. There are 2 cases here. So the first case on the left-hand side is a project with an electricity at $45 per megawatt hour with a load factor at 96%, which means you're operating your electrolyzer all the time. Your electricity is, I won't say expensive because 45 is not expensive, but it's 45. And so you see here, if you increase by 5% your CapEx, it's going to increase by this much the LCOH. If you increase by 5% your energy consumption, it's going to increase by this much your LCOH. So here you can see the energy consumption is a more impactful factor than the capex in that case. Now we take the same electrolyzer with the same efficiency, the same elements, and we set it up in another case where your electricity is now cheaper, but you operate your electrolyzer at only 65%. And now you see that your capex is going to be the driving factors in your LCOH rather than energy consumption. So this kind of analysis helps you make choices on, which type of project design and operation is better for you, and also which technology is going to be best depending on the drivers you've identified in your project. So to conclude, LCOH calculation can be very complex. You need to make sure you have the right data and you define the scope and the reasons why you want your LCOH, so you can add details if needed or stay on a basic calculation. And this helps you to optimize technology identification, optimize, the design of your project, vet your supplier by asking them a lot of questions and make sure they are good for the needs of your project. Reducing financial risk by knowing exactly how much the hydrogen will cost in your project, which leads to higher project success and more probability and chances for you to succeed in securing investment, but also securing off-takers and having a project that's up and running efficiently. We've published a white paper on this topic. You can download it and by scanning the QR code here if you're interested in. And we're going to publish another one in a few weeks about comparing apples to apples for technology comparison. That's going to be detailing and talking about the points I've addressed earlier. And Susanna, I don't know if you want to launch the questions.
Yes, the questions are available in the Q&A feature. So if you want to stop sharing your screen, they'll come up on below.
So sharing the slides, yes, I think we can share the slides. Let me scroll up the questions. So I don't have an LCOH template. And the reason why is, as I explained, I think it's important for you to define your own levelized cost of hydrogen model and make it suited for the needs of your projects. So life cycle of the project is again depending on your project, and it's it depends, but most of the time it's going to be defined by the offtake and the investors, the lifetime on which you want to operate. Well, there are different elements. So first, the lifetime on which you want to operate your project can be for, if you take the example of renewable energy project, could be like 20, 30 years. So that's how long your model can run on. But then for investors, for example, your model is going to be on, 10, 20 years, depending on your investors. And for off-takers, you probably need to have secured off-takes for 10, 20 years. So I would say like the average would be 20 years if you want to get started on LCOH. So, and the question from Bridget, about the adjusting the number of sales for each customers. So we are not adjusting sales for each customer because it's otherwise it's like tailor-made electrolyzers for each project, which is not possible if we want to reduce cost, manufacturing cost, and so on. So really the philosophy here is to tried to run as many cases as possible, identified which is the best electrolyzer. And I mentioned that at the end, there is no electrolyzer that's going to perform the best across all aspects, across all geographies, across all project types. So the idea is to select a configuration that's going to be good for most of the projects, for a certain geography, for example, or for a certain application, and then define another product that's going to be more suited for another type of application or another type of geography, and adjust the characteristic of the product depending on that. Yeah, so question about the subsidies or production tax credit in the capex and operational cost. Yes, this has to be taken into account. So I mentioned that at the end, you need to account for everything. So even if you have, I don't know, subsidies for setting up your production, sometimes, and I know in Canada and in the US, there is also investment tax credit. You can receive either direct subsidies or tax credit for the construction as well. So you need to include that in your cost calculation, because obviously it's going to help you drive down the LCOH in your model. Yeah, and so I have a comment about localized refurbishment of electrodes. And just a quick note on that, because I think it's also an important thing. So John Cockerill's strategy is to deploy manufacturing facilities and knowledge and skill force in major hydrogen hubs that are going to be deployed throughout the world. So that's why we have a footprint in China, we have footprint in Europe, we have a footprint in North America, and we are building a footprint in India and in other regions. The way we see it, obviously, hydrogen is going to be a global market. You're going to move hydrogen. There will be import-export markets for ammonia as well. But for electrolyzers, the way we see it is that the project it's going to need maintenance throughout the whole time of the project to ensure that the system is operating at the right level of performance. It's not going to break down or whatever. So we really think that localizing the supply chain and localizing, so refurbishment, maintenance, spare parts, but also workforce and knowledge in the different areas where there will be a lot of projects going to be really important to reduce the levelized cost of hydrogen on the long run and to ensure that the projects are operating smoothly, rather, compared to if you source your electrolyzer from the other side of the world, and when you have an issue, you need to send it back, pay the transport cost, wait 1 month for it to be repaired, and then have it shipped back again to your project. Just for giving you an order of magnitude, our electrolyzer stack is 5 megawatt, and it weighs more than 50, 60 tons. So if you want to move it around to have it refurbished, you need specific transport infrastructure and so on, and you don't want to be moving it at the other side of the world for just a maintenance routine. Another question about pressurized alkaline electrolyzers. Alexander asked, do pressurized alkaline electrolyzers have sufficient partial load capabilities to make them viable for intermittent renewable energy sources? So yes, it depends on the type of alkaline pressurized, but the way I present it is that alkaline pressurized are the balance between PEM electrolyzers and atmospheric alkaline electrolyzers. So the fact that the electrolyzers are pressurized enables them to follow this fluctuation of loads. So for example, our electrolyzer can ramp up and down by 4% per second from like the lowest load to the maximum load, which is, if you compare with like PEM electrolyzer, I think PEM it's like 1% per second. So we are even like faster than PEM at ramping up and down. And alkaline atmospheric are much slower. It takes several minutes for them to ramp up and down. So yes, and that's something I think that's it's not advertised enough in the hydrogen world because of all the PEM advantages of having a very short start and stop. But the ramp up rate of alkaline electrolyzer makes them suitable and viable for intermittent renewable sources. And by the way, we also wrote some papers about a comparison of pressurized alkaline and PEM electrolyzers, and pressurized alkaline vs atmospheric alkalines, and all the advantages of pressurized alkalines. And all this documentation is available on our website. You can download the PDF if you want more information. Okay, we have a question about the efficiency decrease over time due to stack degradation. So usually it's a percentage per year, but obviously it depends if you're using your electrolyzer all the time or not. And the stack degradation, as I mentioned, is linked to the way you operate your electrolyzer. So if you do a lot of start and stop and a lot of fluctuation of load, the degradation might be higher. I cannot talk for PEM because it's been recently said, and that's not me saying that, has been reports by Bloomberg New Energy Finance that the degradation for PEM is higher than expected. So I don't know the latest numbers for PEM, but for alkaline, the average is around, it's less than 2% and it's around 1% depending on the suppliers. It's 1% per year if you operate your electrolyzer on a stable load. Okay, so big hitter is electricity energy cost. What can be done to get this down? So that's a good question. I think this is an important question. I think this is really linked to the way you're going to design your project, the location of your project. And I think this has to be taken into account very early on when you're designing the project. So as I mentioned initially, having a project that's, for example, if you plan on using renewable energy, having a project that's located in an area where you have very good energy resources, like a very good wind factor or very good solar exposure all year round, then it's going to be to give you a low electricity cost and a high capacity factor for your electrolyzer, which is going to be good. But then you probably still need to be connected to the grid or to have like battery system or other storage system for your energy. And that could add cost. So then the next step is to look at what are your options to source this electricity from somewhere else. And if you're close to a substation, if in your region it's easy to get grid connection, if the grid connection cost is not too expensive, then it's a good thing. If you're in a region where you're going to have to set up a new electric line from your project to the next substation, or maybe create a station, if the connection grid cost is very expensive, that could really be damaging for your project and even just condemn your project because you will never be able to get a good LCOH if your electricity is too high and you cannot get this cost down. So really designing your and knowing your electricity input from the very beginning of your project is also a very big item for you to get a low levelized cost of hydrogen. Okay, so LCOH of green hydrogen compared to LCOH of blue hydrogen. So I cannot answer that question, but blue hydrogen is in the latest studies is still cheaper than green hydrogen. But again, it depends on the geography and the location of the project, and if you have carbon tax, if you have carbon credits. And then, yeah, I think there is a discussion, I haven't read all the comments, but about the SOEC technology. So another thing I didn't talk about is the TRL of the technology. As for now, when you look at all the projects that have been deployed worldwide, the largest projects in operation are using alkaline technology and alkaline pressurized technology. The two largest projects in operation today are in China, and they've been supplied both by John Cockerill electrolyzers and other suppliers, but all of them using alkaline pressurized electrolyzers. And those are like industrial scale hydrogen production projects that are more than 100 megawatt each. And those are the two largest projects. Then when you look at the other projects that are in operation, they're all below that 100 megawatt level, and they're more in the range of like a few megawatts, 20 megawatts, 30 megawatts. PEM technology, the largest project in operation is in Canada right now, in Bécancour, and it's 20 megawatts. Just to give you an idea of the range of magnitude between PEM and alkaline, and those are the two most advanced and ready technology for large projects. SOEC is very promising because of the high efficiency, but on the other hand, there's still a long way to go until they can supply for projects of like 100 megawatts, 1 gigawatt even, and the scale of it is it's not going to go from like a few kilowatts to 10 megawatt units or 100 megawatt units in just a few years. So if your project you want to have it deployed in the next 2-5 years, I would recommend you to look into more established and proven technologies like alkaline pressurized, and PEM, rather than SOEC for short, medium-term projects, especially if they're large. I think we have 2 minutes left. So I'm just looking at another question. Okay, share quickly the presentation with I've seen the question about the QR code. Yeah, here it is. And I think we'll end it here. Susanna, thank you very much for attending and for the interesting questions. I hope it was helpful for you. And thank you, World Hydrogen Leaders, for making this organization of the webinar possible.